my name is Sebastian Weidt. I'm co-founder and CEO of Universal Quantum, and I'm also a lecturer in quantum technologies at the University of Sussex in England. And I'll spend the next 30 minutes roughly telling you a little bit about quantum computing, what quantum computers are, roughly how they work, and also give you a flavor of what they may be able to do for us, and on what sort of timescales we're talking, and also predominantly what we're working on at Universal Quantum, how we're building these machines and what they look like. So I'll try and keep this talk quite light on the quantum. I hope you guys will be able to follow it, but I will be available in the Q&A afterwards as well if you have any questions. So maybe to start, let's start with a little bit of quantum weirdness, so to speak. So the first thing to notice, and when we talk about quantum computing, we need to look a little bit about at quantum physics. And quantum physics is basically the law that governs the very, very small. So if you zoom into your table and you, for example, go into the atomic scale, what happens on that sort of scale is basically governed by quantum mechanics or quantum physics. And in this strange world, some really, really weird counterintuitive things happen. So for example here, and by the way, if you're wondering, this white dot on the screen that's slightly moving around there, that's actually a single trapped ion. So an individual particle we're looking at there. Now, in this weird quantum world, the sort of things that can happen is that, for example, this particular ion that you see here on the screen could actually be in two places at the same time. It could, for example, tunnel through a solid wall, or it can exhibit this entanglement, which some of you may have heard about before, which is something very strange. Einstein, for example, didn't believe in it for a very long time. He called it spooky action at a distance, but it's actually something that nowadays we can generate in the lab, and is actually at the foundation a lot of the technologies that we develop. Now, over the years, what's really happened is that especially at the beginning of academia, people got very good in controlling these quantum systems, or for example, controlling these individual charged atoms or ions that you're seeing here. And with that exquisite control, you basically got the ability to make something be in two places at the same time, or entangle something at the press of a button. And with that, it was basically possible to think about what useful thing we can do with that. What sort of new technology could we develop with that sort of level of control? And with that came a broad range of new technologies that people are currently working on. Quantum computing is a big one. It's one that I'll be focusing on during my talk today. But there are other called quantum technologies out there, for example, quantum sensors. So these are very, very sensitive sensors that can detect maybe magnetic fields or electric fields, or in some cases, maybe even look around the corner. And quantum communication devices is another one. And all of these are currently being developed and at different stages of maturity, so to speak. So for example, quantum communication devices, we're really seeing some of those being pushed into the market. I think quantum sensors are also soon to follow. And quantum computers are really seen as the holy grail in quantum technologies. It's the hardest to achieve, the longest time horizon that we're looking at, but it most certainly has the biggest upside and advantage to us as a society as well when they become available. Now, a little bit about quantum computing. So on a high level, quantum computers really form a completely new technology, a new type of technology that has little to do with conventional computing. Although in my talk, I will try to relate some of the functionality of quantum computers to conventional computers, but it's important to know that they work quite differently. Nevertheless, the development of quantum computers may actually follow a very, very similar trend to conventional computers, and I think we're probably right now where conventional computers were in the 60s maybe. Now, why bother is maybe a question. What do I need a quantum computer for? And quite often, you may have heard about this as well. What people often refer to as a motivation for quantum computing is that it's becoming harder and harder to keep Moore's law alive. And I don't think I need to cover here what Moore's law is, but the point is really that it's become pretty common knowledge that it's very difficult to keep up with Moore's law, and there may well be a limit to how far we can go with increasing our computational capabilities that we have. I, to some extent, have a problem with this particular argument because it would imply that quantum computers are just expected to keep Moore's law alive, and this is really not the case at all. And I hope that that's also something that will come through in my talk today. Really, when we start thinking about this sort of field, what we should really ask is what can a quantum computer really do? And in a nutshell, what we can say is that it's expected to be able to solve certain problems which would take even the fastest supercomputer 1 billion years to solve. And this is really where my comment comes in regarding just keeping Moore's law alive. This is not what this technology about. This is really a significant step change. These are problems that these machines are meant to solve that you would never trouble a conventional computer with. Now let's see how quantum computers are meant to be able to do that. How we're hoping that they will achieve this. Now, when we look at the fundamental building blocks of a conventional computer, for example, and you will all know this, no doubt, is that we have conventional classical bits, which store information in strings of zeros and ones. Now, in a quantum computer, we actually have something similar, but we don't call them a bit. It's a quantum bit or a qubit. And because these qubits live in the quantum world, we can actually have these zeros and these ones represented at the same time. So, for example, bit, and I think I do this on the next slide. Let's say I have a 2-bit conventional computer. What I will be able to do is represent a number such as 0, 1. Or I could have 1, 1 if I wanted, or 1, 0, and so on. Now, in a quantum computer, where I have, for example, 2 quantum bits, I can have all of those 4 possibilities at the same time. And you can maybe already see that this may be quite significant. To make this a little bit more obvious, if we, for example, look at a 100-bit computer, then I can have a 100-bit string that I can represent, whereas in a quantum computer, I can have, and I'm not even going to try and read this out, but I can have this many different numbers all at the same time. And to really sum that up is that in general, the computational space that you have available scales as 2 to the power of n, where n is the number of qubits that you have. So it very, very quickly becomes a very, very powerful system that you have available there. Later on, we'll get on to why 100 qubits, for example, is not the end of the story, but this gives you a flavor of why quantum computers work quite differently and also maybe hold quite a significant advantage over conventional computers. Now, when it comes to the operation of a quantum computer in a high level, it's actually not so different to a conventional computer. So we also run algorithms, quantum algorithms. Now, they are quite different to conventional computers, but they're just a series of instructions that the quantum computer performs. And it always starts with an initialization stage. And then we input the data, whatever data you'd like to process. And then we go through a series of processing steps to process the information following the quantum algorithm. And at the end, we have an output state, which we read out. Now, because this is all quantum, you can maybe already see this, that I input the bit string of information. During the quantum processing, during this evolution, I have access to the full quantum computing space. So let it be 2 to 100, for example, or whatever the size of the quantum computer. But at the end, when I actually want to read out the information, I need to interact the quantum computer with the classical world, and it becomes a single bit string of numbers again that outputs the answer of the particular algorithm. Now, when we think about what sort of applications quantum computing may have, I think it's probably fair to say that we are only at the beginning of understanding what these machines will be able to do. Nevertheless, we already know a broad range of application areas, and I've listed a few here. And it goes across a range of pretty exciting areas. So, for example, the development of new pharmaceuticals. And this really comes from the ability of quantum computers to, for example, simulate chemical reactions better. And one way of understanding that is that in the way I try to understand it most certainly is that chemical reactions, we're down into the very small scale, the molecular scale, for example. It's very difficult to understand the reactions that go on there for a conventional computer, because it's inherently quantum. Whereas using a quantum computer to understand a quantum system makes it a lot more efficient to handle these sort of problems. And we already have a number of quantum algorithms out there where we know that they will have a big impact on this sort of field. And we then go on. We know that there's a lot of interest in the financial sector with some of the algorithms that we've discovered, developing new materials, machine learning, and I will say a little bit more about that as well. And which may also be relevant to you. I don't find it so exciting, but breaking encryption is always something that people mention when they talk about quantum computers and their applications. It's really the ability of quantum computers being able to factor large numbers, which a lot of our encryption protocols rely on, that conventional computers aren't very good at, whereas quantum computers really like to factor large numbers, and down the line will most certainly be able to break our standard encryption protocols, such as the RSA encryption. Let me move on from this. So I just wanted to also, given the audience, I thought maybe machine learning is something that is of interest to some of you, just give you a little flavor of a particular application area. So when we talk about machine learning, and I'm most certainly not an expert in machine learning, but when we mix machine learning and quantum computing together, there's actually a pretty vibrant field and interest at the moment in quantum machine learning. And the way you can think about this area is that you can, have the classical case where you have classical data being matched with a classical algorithm and doing some machine learning that way. You can most certainly also have a classical algorithm working with quantum data, and this is when we're talking about conventional machine learning algorithms actually helping us to optimize quantum computers, and this is already something that is happening. We also have the case where you could use a quantum algorithm on classical data and do some quantum machine learning on the sorts of data that you may be working with today. And then there's also the pretty far in the future case where we have quantum computers working on quantum data, and you can most certainly envision that you could use a quantum computer to make the next generation of quantum computers more efficient or more powerful, for example. But currently, the most of the focus is really on applying quantum algorithms on conventional data. And just let me give you an example of where we are there currently. So in the simplest way, the way I understand it at least, is that in machine learning, what we really often like to do is to solve systems of linear equations. And it turns out that this is actually something that quantum computers not only like to do, but it's part of how they operate. Quantum computers are very, very good in implementing matrix operations, manipulating large vectors in very high dimensional vector spaces. This is actually how quantum computers can mathematically represent it. So there's a very nice link between the two fields. And if we, for example, look at the area of support vector machines or carrying out projective simulations, we already know that, for example, the HHL algorithm, which is a quantum algorithm developed, which is at the foundation of quantum algorithms that have applications for support vector machines and projective simulations, that algorithm can solve linear equations exponentially faster than the conventional means currently being used. And it is largely due to that algorithm and a number of other ones, which make me very excited about the prospect that quantum computers quantum computers being around in the future and being able to significantly impact this area. Now, a fair question to ask right now would be, okay, great, I understand quantum computing is all very nice, but how do you actually build these? What do you use to make a quantum computer? What do they look like? Now, because we're talking about quantum and quantum computers, we need to look for something very small. We need to look for a system which can exhibit these quantum effects that we talked about. And currently, the two leading platforms, the two leading quantum architectures, so to speak, that people are following and working hard on are superconducting qubits, which are basically computer chips specially developed for this area, which you cool down to near absolute zero, so close to minus 273 degrees Celsius. Another way is to use individual charged atoms. You've already seen one. It's something that's close to my heart, and we work with a lot, where you use individual atoms to encode information inside of, and then make use of the quantum world that these atoms exhibit to process the information. And this is a largely room temperature technology, which is one of the reasons why we like it a lot. If you haven't heard of quantum computing, it may surprise you. The number of large organizations involved in building quantum computers, and it really covers a whole range of the large top organizations out there: Google, Microsoft, Intel, IBM. The list goes on, and almost weekly or monthly, you hear about new, big organizations getting involved in this game. But equally, you also see a very vibrant startup scene being involved in this. Often startups from leading academic groups around the world, trying to use the way of the startup scene to commercially build the quantum computers that they maybe previously developed in academia. And some of those are Rigetti, IonQ, RSSY, Universal Quantum, and a number of other companies out there. Now, here I'm very much focusing on hardware developers. There are also some software only, so quantum software only companies out there. But since this is a bit closer to what we're talking about today, I just thought I'd focus on these. And it's most certainly important to note that all of these companies have their own software effort as well to actually be able to operate these quantum computers. Just a very, very quick note in case you are interested in what the difference is between these two leading technologies. And I should say there are a number of other technologies out there, photonics, etc. But currently, by going by key metrics that one has to use when thinking about how good a quantum computer may be in the future, these two are the leading ones right now. And the reason we really like trapped ions a lot is that it is a naturally room temperature device, which makes us believe that it's simpler to scale this technology up. It's also already done a lot of work in understanding the engineering involved to scale up, and we've very much been involved in that, and I'll say a little bit about that later. And a simple but key one is that atoms are generally the same. They're completely identical. They can be, and a terbium atom is the same here in Brighton, where I'm right now, as it is in San Francisco, in Hong Kong, or wherever you may be. Now, this helps when you realize down the line you need lots of these qubits and you have to carefully control them. Whereas in the superconducting qubit world, they have to manufacture these qubits individually, and they are not all identical, which makes their life a little bit more complicated. So just to give you a flavor of what this technology really looks like, this is one of our quantum computing microchips that gets fabricated in your standard MEMS type fabrication facilities, and you can see these white dots at the top right corner again, which form our ions and form our qubits for our information processing. And these qubits or trapped ions, they hover roughly 150 micrometers above this microchip, and we can then apply specific control signals to, for example, move them around, to bring them into a storage zone, a memory zone, or a processing zone, and so on. And I'll have some animations of this later on as well. This is what a messy quantum computer, small-scale quantum computer, looks like. That we, for example, operate, and we have, I think now there's 6 of these machines. It looks messy. It is messy. I call it an organized mess. But so this gives you an idea of what these machines roughly look like. Now, this is still in the academic setting, and Universal Quantum is building their own machines at the moment, which I suspect might look a little neater when it's not built by PhD students, postdocs, etc. But at least here it's all very exposed, and you can see that there's sort of bare subsystems involved in making these machines work, lasers and optics and frequency generators, etc. So a good question to ask right now is, well, what's missing? I've just showed you a small scale quantum computer. It all sounds really, really exciting and great. So why don't I have a new drug yet that was developed using a quantum computer, for example, or a new material? And the main reason, as is often the case, is really scalability. And by scalability, I mean increasing the number of qubits to a sufficiently large number that we can perform operations required to, for example, develop a new drug. And this would be a good point for you guys to stop me, because early on I said to you, look, with 100 qubits, you're already there. You've got 2 to the 100 different states you can represent simultaneously. Surely that would be enough. And you would be correct in saying that. Now, one of the big challenges in quantum computing as a whole is that we aren't perfect at making these quantum operations, at performing these quantum algorithms. We introduce errors into the operation unintentionally, and this actually then puts a limit at the sort of operations that we can make. Also, it's actually not that easy to get lots of these qubits. It's very engineering challenging. But one of the key things I want to focus on here is this error rate, because the interesting bit to mention is that similar to conventional computing, we have error correction protocols that's also been developed for quantum computing. So we have developed methods to correct errors during a quantum operation, and the error threshold, so to speak, so above which we would be able to distill a quantum computer up to doing perfect quantum operations, is roughly 1%. So we can tolerate errors of around 1%. The downside is that the closer you get to this 1% error, the more qubits you need to carry out this error correcting. And with reasonable assumptions on the sort of error rate that we will have with these larger machines, we currently estimate that we will require millions of qubits. And that's a lot of qubits, given that currently we work with tens of qubits. So this is really a key challenge that Universal Quantum is very much focused at solving in scaling our technology up to those sort of qubit numbers. Now, a nice visual summary of this is basically given here by John Martinez, where you can see this hopefully in a slightly clearer way. Now, I don't have a laser pointer, but currently we are where number 1 is. We've recently heard the announcement from Google, for example, that they reached quantum supremacy. So for the first time, a quantum computer has done something that even the most powerful conventional computer was not able to do in that time frame. A really key milestone, but one should also say a largely academic milestone that was ticked for, but a very, very important one. Now, what you can see here is that where we'd really like to be is number 4. 4 is really the end goal. This is where we have a large number of qubits and a sufficiently low error rate that we can carry out error correction protocols. Now, the near-term application, the blue that you see in the middle, is really an interesting area that people are focusing on a lot right now, and trying to come up with near-term applications using the machines that we currently or will have available in the next couple of years. And a lot of work has gone into this and is starting to give some results. And I think this will be very interesting to monitor how this will progress. And it's really one of the the main reasons why you see a lot of the big players getting involved. It's so unpredictable at what point a quantum computer will really start to add significant value to a more traditional field like banking or the pharmaceutical space, that people want to stay very close to this technology, maybe even support the development of these quantum computers, such that when these machines will start to produce something useful, they're right there to take advantage of it. Because the step change is so big that if you do fall behind this technology, you can easily be put out of business just because of the advantages that this technology comes with. So just as a very high level overview, if you're interested, how do you actually build a large scale trapped ion quantum computer? What is this gonna look like? And in 2017, actually, and that was work led by us, we actually developed the world's first blueprint for how to construct a quantum computer with millions of qubits. And it was very much an engineering focus that we followed during that collaboration, and Google was part of this at the time as well. But the work really culminated in this modular architecture, where we are, and you can, I don't have a pointer here, but you can maybe see at the top is where the quantum layer is. So these trapped ions forming these qubits, they levitate above a quantum computing module. And below that is a whole lot of electronics that's being integrated into the module to form fully functioning individual quantum computing modules. And we've then developed a method to connect individual modules, which will allow this technology to scale up to, in principle, arbitrary numbers of qubits. This may look very abstract to you, but if you actually were to take one of your favorite IBM processor chips, and you were to slice it open and have a look at what they look like, then what you realize is you have layers of transistors and lots of wiring going around. And I'm not saying it's the same by any means, but in a way we have something similar here. That the ions or the qubits make the transistors that we have at the top, and then there's a whole lot of electronics going on to make sure that all these things move around correctly. Just to give you a feeling what this really looks like, here's a fly-through of a large-scale quantum computer, where these red and blue balls, they are the qubits that we can move around between different processing zones or memory zones. You can ignore some of the technical detail shown here, but where we are right now is a processing zone where we implement the logic gate operations that make up a quantum algorithm. And at some point, once you've carried out the operation, you may want to extract the information that these qubits now hold. So you go into a readout zone, and then we have a specific detection scheme that will actually allow you to turn this quantum information, so to speak, into classical information that we can read out and interpret. We then zoom out a little bit, and this is actually an error correction protocol running here at the moment. You don't have to worry about the details so much, just to say that we then get to these individual quantum computing modules where we have integrated all the necessary electronics and done all the required engineering, such that these are standalone quantum computers. So we integrate the FPGAs and everything required to do the backend operations. And once we've done that, you then simply align these modules in such a way that you can physically transport these qubits between individual modules. And this is very key for us. With this sort of approach, we can make sure that the connection rates between modules are as high as possible. That's absolutely key to the operation of a quantum computer. And once one has reached that sort of stage, it then very simply just scales up. One should say that this is further in the future, and we're by no means close to this stage yet, but just to show that the engineering approach that we're following does scale up to the millions of qubits, which is where we need to be and what we are very much passionate about getting to. Now, Universal Quantum, haven't really had time to talk about this company a lot, but it's really at the heart of doing the engineering required to build these quantum computing modules, and in the end actually build a large-scale quantum computer. It is a spin out of the University of Sussex, and its core mission really is to build quantum computers that will allow you to eventually develop new drugs, etc. Just to summarize this quickly, the take-home messages should most certainly be that we are now at a point where it is technically possible to build a large-scale quantum computer with trapped ions, and I've shown you some of the ways we think that can be done. Quantum computers, no doubt, have incredible potential to transform science and society. In a positive, also in a negative way, but there are huge upsides to this technology. Nevertheless, and I'm not a big fan of hype, this is highly challenging. It will most likely be seen as one of the machines of the century when we look back in maybe 10, 15, 20 years. But it's just so incredible what this technology will be able to do that we and others most certainly feel absolutely worth doing the hard work on this side. One thing I wanted to point out, also given the forum here, is that in order to do this, you don't just need quantum physicists running around trying to build this machine. And really, and this is where universal quantum really comes in as well, it's making use of the incredible engineering, software, business talent out there, and bring them together to form a very unique team that will be able to pull this off and build these incredible machines. And I think in the end, what we're already seeing is that we're moving somewhere where we're going to have quantum engineers, quantum software developers, quantum business developers. So these are not people who've come out of universities with a physics degree or some quantum related degree. These are people who, have done very well in their particular area and now want to apply their knowledge to this particular field where a quantum background is most certainly not required. And I can also say that in Universal Quantum, for example, we haven't hired a single quantum physicist, apart from me maybe. But all the engineering talent that we've brought on have no quantum experience. And I think this is a very good sign and a testament to this technology really being ready to be commercialized, which I think is incredibly exciting. Now, to leave you with a thought or a question, I think given that this is such a different technology to what you may have experienced before, maybe have a think about, what an unbelievably fast computer, which, arguably is executing operations in parallel universe, could do in the area that you work or live in. Thank you very much.